All right, I think we're going. Usually it gives me a countdown, but I was waiting for it and I didn't get a countdown. So, welcome to Scale Models Lesson 2. Again, I'm using the old PDF, so let me just quickly change this. Scale Models Lesson 2. So last lesson we looked at scale factor and using our scale factor equation, which is scale factor is equal to new over original. So let's look at scale diagrams. You guys will be doing, or you all will be doing a scale diagram project at the end of this. So this is a good one to pay attention to because we will be using scale and making a diagram. So that'll be fun. So it says here, great white sharks can grow to a length of approximately 6.5 meters. The diagram is a scale drawing of a great white shark. So it's not the right size, but it's drawn to scale. Excuse me. To determine the actual length of the shark, we need to know the scale used in the diagram. So by how much has this been reduced, basically? So the scale can be given in a few different ways. So we will talk about first a statement. So just using English, and we can say that 1 centimeter in our diagram represents half of a meter in real life. So that's your scale. And you can see we're using two different units. We're using centimeters and we're using meters. We can do it as a rate, so a ratio or a rate. So a rate is basically a ratio, but we have two different units still, 1 centimeter and 1 meter, or we can do it as a fraction. 1 centimeter over is representative of 0.5 meters. If we wanted to convert that to an actual ratio, we would have to use the same units. So you can see that if 1 centimeter is representative of 0.5 meters, what we want to do is convert that meters, those meters here, into centimeters, because you can see our ratio over here is just 1 to 50. There's no units because they're the same units. So we either need to convert that 1 centimeter into meters or that 0.5 meters into centimeters. So you can do a unit conversion if you'd like, 0.5 meters. We're going to multiply it by a conversion factor. So in this case, we have meters in the top, so we'll put meters in the bottom, and we're trying to convert it to centimeters. And now we just need to fill this out. So if we have 1 meter, how many centimeters are in 1 meter? And we know that's 100 centimeters. So now we can multiply everything in the top and multiply everything or divide everything out of the bottom, but we know the bottom is 1, so we don't actually have to divide. We just have 0.5 multiplied by 100, and that gives us 50 centimeters. So we know that that's the same. Now we can rewrite that 0.5 meters as 50 centimeters. It's the same thing. And since we have the same units, we can just write that as 1 to 50. And you're going to see these scales on maps quite often. And we'll talk a little bit more about that. We have a map question on the next page. And then what you definitely see on maps is a line graph scale. So it's the same thing. It would actually, in real life, if you measure this would represent 1 centimeter. And so it's saying, well, 1 centimeter is equal to, from here to here, 0.5 meters. And so it's just kind of like giving you more of a visual for that. So let's use this information. It says the lengths of sharks are generally measured from the tip of the nose to the middle of the tail. Measure the length of the shark in the scale diagram and use proportional reasoning to determine the actual length of the shark represented in the scale diagram. So we're going to do two methods here, and you choose whichever one you like, whichever one makes sense in your head. I will show you both. So one's going to be using the scale factor equation, and one is going to be using proportional reasoning. My spelling is not good. Reasoning. So if we head back up, if my computer will let me go back up, there we go. And we measure the shark from the tip of the nose to the middle of the tail. We'll pretend I have a ruler. I know that that will represent, I have the answer key, so that's how I know. 9.6 centimeters. I'm going to skip actually measuring it. You wouldn't be able to see me do that anyways. So we know that the shark is 9.6 centimeters, and we know that our scale is every 1 centimeter equals 0.5 meters, or you can think of it as 1 centimeter and 0.5 meters, or you can flip that fraction if you'd like. 0.5 meters is representative of 1 centimeter. So you can see here that if we use the scale factor equation, we know scale factor is equal to new over original. And we're trying to find the original length, right? The new length is our scale length, which is, this is our new one right here, 9.6. And any of these three represent our scale factor. So what we're trying to find in this equation is the O, the original. So if you do a little bit of algebra here, multiply both sides by O, that cancels out. We're left with original multiplied by scale factor is equal to new. And then we can divide both sides by scale factor. Just using algebra to manipulate this formula a little bit. Scale factor cancels out. And I'm left with original is equal to new divided by scale factor. You could also just plug the numbers in and then do algebra after. It'll work out to be the same. So the original length is going to be, well, 9.6 centimeters divided by, well, our scale is 1 centimeter over 0.5 meters. And when we do that in our calculator, so what I would do if I was you, just to go over this, I would go 9.6 divided by, and then in brackets, 1 divided by 0.5. Those brackets are very important because you want that 9.6 to be divided by all of that. So that's how you type it in your calculator, and you should get 4.8. And we know the original is going to be, well, we know that our scale factor is converting centimeters into meters, so our original should be in meters. That shark is 4.8 meters. Proportional reasoning I find is easier to wrap your head around a little bit. So same question, pretend like what we just did didn't happen. And I would say, okay, well, my scale factor is 1 centimeter is equal to 0.5 meters. And then I'm going to set it equal to proportional reasoning. It's going to be two fractions. So now I'm going to say my diagram is 9.6 centimeters. And I don't know how many meters. So I'm going to say maybe X meters. Actually, let's use a question mark. Okay, here we go. Question mark meters. So you're saying, well, I know my scale factor is 1 centimeter, is representative of 0.5 meters, and my actual diagram is 9.6 centimeters. How many meters does that represent in real life? And then what you're going to do is cross multiply. So basically what happens is this moves up to this side, and this moves up to this side. So you can say we have 9.6 multiplied by 0.5 is equal to 1 multiplied by our x, right? Our unknown, which we can just make, we don't even have to write that 1 in there because 1 times anything is just itself. So now 9.6 multiplied by 0.5 is 4.8 meters. Same answer. Two different methods, same answer. I personally really like the scale factor equation because it works for everything. If you can figure out which one's your new, which one's your original, and which one's your scale factor, you can manipulate your formula to find that, right? Because we know scale factor is new over original. We know that new, if we manipulate that formula, is equal to scale factor multiplied by original, and we know original is equal to new divided by scale factor. There's three equations that you can use right there. Okay, moving on. Here is our map. You can see that we have a line graph scale right here. So we know that each of these increments right here is 1 centimeter. So you can say that our scale is going to be 1 centimeter represents 75 kilometers. And that'll change from map to map depending on how big it is, right? So it says here, use the line graph scale to determine the approximate straight line distance between Calgary and Edmonton. So let's figure that out. We have Calgary down here. We have Edmonton up here. So we want to draw a straight line, which pretty much represents the highways in Alberta because they have no mountains to go around. So if we measure that with our ruler, we know that that is 3.6 centimeters. So you can use either method that you would like to solve this, because we know that 3.6 is our new, or our scale, and our scale factor is 1 centimeter to 75. So what you could do is scale factor is equal to new over original. We are solving for the original. So we know that the equation is going to look like original is equal to new divided by scale factor. And so I can plug everything in. I'm looking for original. My scale is 3.6, and I'm going to divide it by 1 over 75. And when you do that, you will get 270 kilometers. So that is your straight line distance between Calgary and Edmonton, right? It's not going to be 3.6 centimeters. We know they're a lot further away than that. But in kilometers, according to our scale, it's about 270 kilometers. If you were to do proportional reasoning, you could do, just to show you the other method, you can say, well, I know that 1 centimeter is equal to 75 kilometers, and that will equal, well, on my map, the distance is 3.6 centimeters, and I don't know what the kilometers are. We'll use maybe an X this time. X is always good because it represents an unknown. And then the only thing that's important when you do proportional reasoning is that if you have centimeters in the top of this one, you need centimeters in the top of that one, and then kilometers in the bottom and kilometers in the bottom. They need to match. So we'll do our cross multiplication. So now we have 1 times x is equal to 3.6 multiplied by 75. 1 times x is just x, right? It just doesn't change. And then 3.6 multiplied by 75 is 270, and we are in kilometers now. Same thing. I know that proportional reasoning seems a little bit quicker and easier, but I think using the scale factor formula is going to be more applicable as we move forward. Okay, calculate the approximate straight line distance between New Hazelton and Prince George. Maybe we'll actually do this one in class. Remind me that we're going to do this one in class because I'm making this video a few months in advance. And this is a good example to do in class, but I probably won't remember. So just remember, just put your hand up and say, Mr. Sadler, you said we were going to do one of the map questions in class, and then we will. Okay, let's get on to some practice problems here. So it says here, Tyler's scale diagram of a tower is shown. So the actual tower is 240 meters tall. So that's the original, right? We know that that's the original. That's the actual tower. Write the scale Tyler used in statement form. Okay, so, well, let's have a look here. If we measure this from top to bottom, it's 8 centimeters in real life. So we can say 8 centimeters represents 240 meters. Sometimes it's nice to simplify that fraction, right? If we know 8 represents 240, can we reduce that fraction? What does 1 centimeter represent? So what we can do is, I'll use blue here, divide both sides by 8. That's a little arrow, sorry. Divide by 8. So to reduce a fraction, you want to divide the top and the bottom by the same value. So 8 divided by 8 is 1, and 240 divided by 8 is 3, which is perfect. So that means that 1 centimeter represents, that's 30. Sorry, did I say 30? Hopefully I said 30. Represents 30 meters. So according to our scale, if this is an actual scale diagram, 1 centimeter represents 30 meters in real life. So as a rate, we know a rate can have different units. Let's maybe do that in green. But a ratio has to have the same units. That's the difference. Okay, so as a rate, we would say 1 centimeter is 30 meters, or you can do it as a fraction if you wanted to. 1 centimeter is 30 meters. When we write it as a ratio, we want to have them in the same units. So it's actually easier to convert the meters than the centimeters. So we know the rate is 1 centimeter is equal to 30 meters. And we just want to make them have the, or convert them so that they have the same units. It's easier to convert the, hang on, undo. I thought I had my highlighter out. It's easier to convert the meters into centimeters rather than the centimeters into meters, because it'll give us a weird decimal. So we want to convert 30 meters. And so we'll multiply that by a conversion factor always. We want it to be in centimeters, and we want to get rid of the meters. So there's meters in the top and the bottom, and they end up canceling out. And we do that by design. We just need to fill in the numbers now for centimeters and meters. So I always say, okay, well, if I have 1 meter, that's 100 centimeters. And you can always use any conversion factor as long as they're equal, right? You can use 2 meters is 200 centimeters if you want to, because that's just 1, right? That just equals 1. It's the same. It's just like 200 centimeters and 2 meters are the same thing. It's just easier if you use a 1 on the bottom of your fraction, because then you don't have to do any division, right? We know 30 multiplied by 100 is going to be 3,000 centimeters. So now we can rewrite this as 1 to 3,000. And we don't have to put units in because they're the same units. Hopefully that makes sense. Okay, let's do this last problem here. Kylie from Abstract Renovations designs a plan for a candy store to be renovated. The scale drawing on the plan of the candy store is 1 centimeter is equal to 50 centimeters in real life. So that's our scale factor. And it already has the same units, which is fantastic. So what are the actual dimensions of the storage room if the scale diagram dimensions are 8 centimeters times 12 centimeters? So we know that the store on the diagram is 8 centimeters multiplied by 12 centimeters. And what we want to do is convert those into the real dimensions, right? Because that's on the drawing. So what these represent are the scale or the new. And what we're trying to find are the actual dimensions or the original. So if we're trying to find original, we know our formulas are scale factor is new over original, new is scale factor multiplied by original, and original is new over the scale factor. So we're looking for the original. We are going to use this formula right here. The original is equal to 8, which is our new, divided by our scale factor, which is 1 over 50. So again, if you're typing that in your calculator, you go 8 divided by bracket 1 divided by 50 bracket. And what you get is 400. Is that 400 centimeters, 400 meters? Take a second and think about it. Hopefully you said centimeters. Everything's done in centimeters, right? We know our scale factor is centimeters to centimeters. So that's 400 centimeters. We're going to do the same thing for 12. We have to convert both dimensions, right? It's like saying on the drawing, we have the room. It's 8 centimeters by 12 centimeters. But in real life, so this is our scale, this is our original. In real life, what are the actual dimensions? Well, we know this side is actually 400 centimeters. And now we're just trying to figure out what that dimension is. So we will convert that 12. We're going to use the same formula. Original is equal to new divided by scale factor. So we can say 12 divided by 1 over 50. And that gives us 600 centimeters. So we know the room is 400 centimeters by 600 centimeters. But that's not super awesome because it's hard to visualize 400 centimeters and 600 centimeters. So what you could do is convert that. Maybe I'll just use this space down here. If 1 meter is 100 centimeters, which is something you should all know and memorize. If 1 meter is equal to 100 centimeters, that means 400 centimeters represents 4 meters, and 600 centimeters equals 6 meters. I apologize for how messy my writing is. My pen is not super, it's a little bit too sensitive. So I've ordered a new pen. It's just on the way. It should be here hopefully tomorrow. So anyways, if 400 centimeters is 4 meters, 600 centimeters is 6 meters, then we can say our new dimensions are, or it's the same dimensions in a different unit, right? Our room is 4 meters by 6 meters. That makes a little more sense. Both answers are correct. What are the dimensions on the plan if the dimensions of the chocolate section of the store are to be expanded to be 3.5 by 4.75? So now we know the original, and we're trying to find the dimensions on the plan, which are the new, right, or the scale. So I put a little question mark saying we're looking for the new. We still have the same scale factor of 1 over 50. So if we're looking for new and we have the original and the scale factor, we can use this formula right here. So now I can say, well, nu is going to equal, we have to do it for both dimensions, so we'll start with the 3.5 multiplied by 1/50, and we will get, what do we get? Just want to make sure I'm doing this right. I should have grabbed my calculator. Give me a second, I'm pulling up a calculator. .07, and that's in meters. We started in meters, we're going to end in meters. And we can do the same thing for 4.75 multiplied by 1/50, and we will get 4.75 divided by 0.095 meters. And we just want to convert those to centimeters, so we can just do a quick unit conversion on all of them, or both of them, sorry. So we'll multiply by a conversion factor. We're going to put meters in the bottom, centimeters in the top. Same thing for this one, meters in the bottom, centimeters in the top. I'm going to erase this just so that I have some space. And I know that in 1 meter we have 100 centimeters. Remember I said memorize that, it makes life a lot easier. 1 meter is 100 centimeters. So now you can do 0.07 meters. Those meters are going to cancel. And same with those meters right there. So 0.07 multiplied by 100 is 7. So 7 centimeters, and 0.095 multiplied by 100 is 9.5 centimeters. So the dimensions are going to be 7 centimeters by 9.5 centimeters. I mean, you could have done 0.07 meters by 0.095 meters, but when we're dealing with really small measurements, it's nicer to have it in centimeters or. Okay, I know that was a bit of a longer one. I appreciate you sticking around. Thanks for watching. Don't forget to like and subscribe.